the different members of the jury. So we have from Delft University of Technology, Liu Jian. Did I pronounce that correctly? Right. Okay. From École Polytechnique Fédérale de Lausanne, Miguel Fernandez Ruiz. From the University of Liege, Jean-Marc Franson, Vincent de Noël, and Jean-François de Monceau. And obviously, the main advisor, PhD advisor, Boyan Mihail. And without further ado, so we will have about 50 minutes, an hour presentation by John about her work, and after that we'll have an hour of questions by the different members of the jury, and then we'll spend a few minutes deliberating. Okay. Without any further ado, please.
Okay, thank you. Welcome to my PhD defense. First, I want to thank all the jury members for reading my thesis and giving very useful advices. And I appreciate that Professor Jian and Professor Fernandez for traveling to Liege. Of course, I thank all the audience for coming here to support me. The title of my presentation is Kinematics-Based Modeling of Deep Transverse Girders in Reinforced Concrete Frame Structures. And before I start the presentation, I would like to give you an idea how I organized my presentation. This presentation lasts for around 60 minutes, and it covers 6 parts. First, of course, I will introduce the background and set up the objectives for my presentation. And then in the following 4 chapters, from chapter 2 to 5, I will try to achieve these objectives one by one. And then finally, I will conclude on my work. I give some suggestions for the future work. So in this very first picture, we can see it is a very large frame structure. In order to have this open space, this column cannot go down continuously to the foundation. But at the same time, there's very heavy load in this column coming from all the upper stories. And the heavy load needs to be transferred to the rest of the structure. How can we realize this? At this moment, a very good option is to use deep transfer girder. And different from normal girders, we can see normal girders or beams. In daily life, this transfer girder has much smaller aspect ratio, and we express this ratio is a ratio between shear span A and effective depth E. And this ratio is normally smaller or equal to 2.5. It is a very important parameter. I will talk about it more later. And due to the heavy load transferred through these elements, it is very important for the safety of my structure. If this fails, the upper structure it supports might collapse, or in the most worst case, the entire structure will collapse. And of course, in the most common case for deep transfer girder is that it's supported on the 2 ends of columns, and then we have a concentrated load from upper structure. This is the most common case, and it's what I'm going to focus in this presentation. But of course, there are some other cases. For example, here is a transfer girder in the train station of Louvain, and here is another building in Chicago. As we can see, instead of being concentrated, the load is uniformly distributed along the length. And this is a structure in New Zealand. This is cantilever deep transfer girder. It has the heavy load on the bottom stories. And in concrete structures, there are many other structural elements. They are not called deep transfer girders, but they behave in very similar way as in deep girders. For example, we have cut beams in bridges. We have these very thick floor diaphragms in buildings. We have strip footings. We have rafter footings in foundations. All those structural elements, we could actually adapt the theory I'm going to develop in this theory to solve these problems as well. And as I have mentioned that A over D ratio is a very important parameter for deep beams, and how will this parameter affect the loading mechanism of the beam? Here I will demonstrate it the reason by experiment carried out by Kani. In his experiment, he tested a set of concrete beams with A over D from 7 down to 1, and all the beams he tested failed in shear. And if we follow this sectional model, which is based on plane section remains plane, which is a very classical hypothesis, as we can see, our prediction is much lower than what we have seen in the experiment. Why? What's the reason? It's because in deep beams, instead of following the hypothesis, plane section remains plane, we have a direct compression left between the loading point and the support. And this special loading mechanism makes my deep beam much more efficient in resisting shear than slender columns. And and now I want to tell you more about the shear behavior of deep beams. So I want to show you this experiment done in the University of Toronto. It is a deep transfer girder with a very large depth, 4 meters. And at shear failure, we can see we have a almost straight diagonal crack, and at this small region we have concrete crash. Actually, before the test, there was an experiment. There was a competition organized to predict the shear strength of this deep beam, and there were a lot of participants from all over the world. And here is our result. As you can see, this vertical dashed line is experimental result, and the other vertical lines are predictions based on design codes. And those dots represent individual prediction from either industry or university. And we can see very big deviation in all the categories. Which means that even though in the past 60 years, we have been making a lot of effort to study this problem, but still it's a big challenge until nowadays to predict accurately the shear strength of deep transfer girders. But through this diversity, through this deviation, we can also see there are some models that behave relatively better than the others. But this is just a specific beam. We need to look at things from a bigger picture. And in the history, there were a lot of models being proposed, and they were concluded to be good, to be accurate. But obviously, this is not the case. We can see from the competition result. And what is the problem? It's because most of the models, they were actually validated with a very small set of tested beams. Therefore, the conclusion is not objective enough. And the first objective of my PhD work is to evaluate the accuracy of existing models for shear resistance of deep beams using a very large database of laboratory tests. Until now, I'm only talking about shear capacity, and as we can see from here, along the complete shear response, shear capacity just corresponds to a specific point. Of course, this is the most important point. But through this point, we cannot see enough about our structure. For example, if we want to estimate a serviceability on the service load, we need to look at the pre-peak behavior. If we want to estimate the ductility, if our structure is under some accidental load, then we need to look at the post-peak behavior. Therefore, it's not enough just to focus on this single point. Therefore, my second objective is to develop a 1D element for deep beams, combining accuracy and efficiency. Accuracy, I want my model is able to provide this kind of complete shear response very accurately, and at the same time, I want it to be efficient. When I'm talking about efficiency, I'm more concerned about this kind of large structure. It is not very straightforward how to model this kind of large frame. I have both slender beams and deep beams. If I have only slender beams and columns in my frame structure, that's not difficult at all. We can use 1D frame elements everywhere. There are a lot of planetary software we can use. For example, here I say Vector5, and the computation is very efficient. But there's a fundamental problem that the theory background for deep transfer girders is wrong. It behaves totally different from slender beam. Therefore, we can look at the other option. We can use 2D finite elements to model the entire frame. Well, now we can get more accurate results, but at the same time, it is very time-consuming. Or sometimes it's just impossible for us to build the model or run analysis. So this leads to my third objective. I want to use the 1D element I'm going to develop for deep beams together with the normal slender beams to form a 1D model for this entire structure. Therefore, my third objective is to integrate the new model into a framework of frame structures with both slender and deep elements. So with these three objectives focused on solid deep beams, I have neglected a very important case. And this case is actually neglected by most of the researchers. We have such a large beam. Normally this girder has the depth 3 to 6 meters. With such a big volume of concrete, sometimes we can just not avoid to accommodate windows, doors, or pipelines. Therefore, there must be some web openings in a lot of cases installed in the transfer girder. And if this web opening is interrupting the loading path, then what will the transfer girder behave? How will it behave? So my last objective is to propose a model to predict the shear capacity of reinforced concrete deep girders with web openings. So in the following 45 minutes, I will try to achieve these four objectives one by one. My first objective is to carry out a comparative study on existing models, and then I can find out which models are more adequate to predict the shear capacity of deep beams. To realize this objective, first I'm going to do a literature review, and I have looked at 73 papers published in the recent 30 years. I have classified these 73 models into 6 categories. The majority of the research is focused on strata-and-time models, and then I have a lot of artificial intelligence models and numerical models. And then I have 8% upper bound plasticity model, 5% shear panel models, and the smallest portion goes to other mechanical models. I have to mention that in the following comparison, these two, they are not included. Why? The reason is that numerical models, they are not developed, especially for deep beams, and artificial intelligence models, they are based on mathematics rather than physics. Therefore, I only look at models belonging to these 4 categories based on physics. In order to carry out this comparative study, I follow 3 steps. First step, I collect a large database of tested deep beam, and then I implement 10 representative models into this large database. And then finally, I could compare the predicted and experimental shear strength for each of these 10 models. First, here is a large database of 570 reinforced concrete deep beams. And this database was collected by my supervisor, and I just did a little bit of extension. And then here I show you the 10 models selected for the implementation implementation. We have one shear panel model, one upper bound plasticity model, and we have 6 stratified models, and the last 2 go to mechanical models. So instead of looking at the details of each models, I prefer to show you the result directly. Here you can so here you can see the statistical distribution of this value. It is a ratio between experiment and predicted shear strength. If our model is perfect, then this ratio should be concentrated along this vertical line, which corresponds to 1. And if our prediction is at this side, it means it is unconservative. To the right, it's conservative. And associated with each model, we have 3 numbers. The first number is a number of tests. This number depends on the limit of applicability of each model. And now we have the mean value of this ratio. We have the coefficient of variation. And the first impression I had on this graph is that from model to model, the distribution is really different. For example, the prediction can be so widely spread along this axis. But there are 2 models that behave relatively better than others. Which is 7, proposed by Professor Russo in 2005, and the 10th, proposed by Professor Mihailov in 2013. And both of them have the shapes very close to the standard Gaussian distribution, which means there's no big bias in the model. And we can look at the numbers. Here, the Russo model produced mean value equal to 1. And for the other model, we have the lowest coefficient of variation among all the 10 models. As we know, if we want to improve the model, we must make the mean value closer to 1. This is very difficult to do. But if we want to reduce a coefficient of variation, this is even more challenging. Due to the good performance of these 2 models, it is interesting for us to have a closer look at these 2 models. So first, I look at the model by Professor Russo. We have a strut and tie model. Here we have a concrete strut with compression in it. And due to the existence of web reinforcement, we have a statically indeterminate shear system. The shear strength of this shear span is assumed to be contributed by concrete and web reinforcement. The full expression is like this. There are a lot of coefficients in this equation, and most of them are actually derived by fitting with more than 200 experiments rather than physics. And the other model is called 2-parameter kinematic theory, which is developed by Professor Mihailov in 2013, based on experimental observation. Here, in this model, we assume there is a diagonal crack running from the support up to the loading plate, and this straight crack separates the shear span into 2 parts. We have the bottom part behaving like a fan. It opens according to this point, along with the elongation of the bottom reinforcement, and which can be represented by the tensile strain epsilon T average. At the same time, we have this top part, which is assumed to be rigid, except that we have this small region, which is called critical loading zone. Inside, there's a very high concentration of compression. Therefore, we have vertical displacement delta C in this region, and with this delta C, these 2 blocks, they separate from each other vertically. And with these 2 parameters, we can actually express the entire displacement field of this shear span, which actually will turn which actually is a very important tool. I will talk more about it later. And now we can look at the shear mechanism. Along the diagonal crack, we have 4 shear mechanisms. We have the shear contribution from critical loading zone due to the high compression. We have shear contribution from aggregate interlock due to the opening and the slip of cracks. And then we have the contribution from stirrups. We have the double action in the longitudinal reinforcement. And if we look at the vertical equilibrium of this free body, we have the shear force equal to the sum of these 4 shear mechanisms. And if we look at the moment equilibrium, we can easily relate the shear force to the tensile force in the bottom rebar. And how to solve this system? We need the help of this plot. In this plot, the red line represents the shear capacity, which is composed of these 4 components, as you saw before. At the same time, we have this black line, which is the shear demand. At the intersection, our structure reaches equilibrium. Therefore, it is a solution we are looking for. So by now, we already know enough about these 2 models. We can go back to the comparison. We already know that these 2 models they behave very well statistically, but are they physically reasonable? To answer this question, I did a parametric study. I looked at some important parameters, for example, A/D ratio. I looked at the stirrup ratio, the longitudinal reinforcement ratio, and for all those parameters, the 2 models capture very well the trend in experiment. But there's one very important effect. I want to talk about it explicitly. It's called size effect. And I will demonstrate this effect with the help of this experiment done by John in 2007. In his experiment, all the beams are symmetrically, they are very similar in terms of geometry. The main difference is the dimension of the beam. Here is the result. In the horizontal axis, we have the effective depth. The vertical axis, we have the nominal shear strength. We can see when the beam depth increase from 350 millimeter to 1 meter, there's a clear decreasing trend in both beams without stirrups and with stirrups. The shear strength decrease around 15% for both groups of beams. It seems not very big difference, not very amazing difference, but the problem is that in practice we have very large structure. For example, here I show you, it's around 3 to 6 meters. So if we follow this trend, the shear capacity can reduce by 30 to 40%. This is huge. We must take this effect into account in our model. So how are these 2 models behaving in terms of size effect? Here is the result. Obviously, strata-time model totally neglects this effect, and the effect is very well followed by the 2pkt. Therefore, my conclusion for this comparative study is that 2pkt provides accurate predictions. And among the 73 models I have reviewed, most of them, actually almost all of them, they are only focused on shear capacity. Only 2pkt is not only focused on shear capacity, but it can also predict the deformation. And what makes 2pkt so functional, so more functional than the others? It's because it's based on kinematics. As I told you before, the interest by this parameter and this parameter. And here I show you the expression of the displacement at any point inside the shear span. And as we know, at shear failure, on near shear failure, the deformation along the diagonal crack is very important. 2pkt can still produce very simple expression for crack width and crack sleeve. We have another important parameter, which is deflection, which is always measured in experiment. For example, in this slide, we have measured the deflection for 53 simply supported D-beams, and we have plotted it here along the vertical axis. At the same time, we have predicted the deflection of these tested beams based on this equation from 2pkt. We plotted along the horizontal axis, and we can see very good agreement. Not only deflection, even the entire deformed shape for beams with different slenderness at different load level, the 2pkt can still provide relatively good predictions. So therefore, we know 2pkt is a very powerful tool, not only for shear capacity, but also for deformation capacity. But there's a limit for this theory. It can only be applied to simply supported D-beams. But in practice, the large deep transfer girders, they are often continuously supported. At this moment, even though 2pkt is so powerful, we cannot use it. So there's a need to extend this theory. Therefore, we have 3pkt here. The theory background is similar as in 2pkt. The main difference is that instead of having a rigid block, we have two fans here. And this fan, it opens with elongation of the top reinforcement. Therefore, instead of having two kinematic parameters, now we have three kinematic parameters. And maybe it's a little bit confusing for you. We have 2pkt, 3pkt. What's the difference? The difference is very simple. 3pkt is a more general case. So imagine that this strength is equal to 0, and then this fan will be the same as a rigid block, and at this moment 3pkt will be degraded to 2pkt. And similar as 2pkt, this 3pkt is also validated with many tested continuous beams, and very good results were reported in literature. Therefore, I will use these 2pkt and 3pkt as a theory background to develop all the study I'm going to show you later. So immediately with this theory, I can start my second task, which is to formulate a macro element for complete shear behavior of D-beams. Instead of jumping directly to the formulation with these equations, I prefer to show you how the continuous beam fell in the lab. So this is two-span symmetrical continuous D-beam. It's here it is a symmetrical axis, and it has three supports on the two concentrated loads, and the shear failure happens in this shear span. And we can see at shear failure we have a diagonal crack, and we also have a small region with concrete crash. This is very similar as what we have observed in the simply supported D-beams. The main difference is that now the cracks are spread within the entire shear span at both sides of the diagonal crack. It is very similar as what I have shown you in the 3pkt assumption. And to the right hand side, I show you the complete shear response of this beam. And for the macro element I'm going to develop, my target is that I can produce this kind of complete response prediction, including both pre-peak and post-peak. So in order to develop this kind of macro element, I have another look at my theory. my theory background, 3PKT, and now I want to look at it from another perspective of view. Before I express the opening of this fan with the elongation of the rebars, is it possible for me to express the opening just with the opening angle theta? Nothing changes, just the way of expression. Now, instead of having epsilon T1, epsilon T2, and delta C, I use theta 1, theta 2, and delta C to express the behavior of this shear span under double curvature. Why I want to do this is because this will make my formulation of macro elements easier. In this way, I can represent these two spans with two rotational springs at the two ends of this macro element, and the rotation inside this rotational spring is equal to this angle. To maintain equilibrium, of course, I will need a transverse spring. This transverse spring, the elongation in this transverse spring represents a vertical separation between these two parts, which is delta C. Therefore, the equilibrium of this shear span, we can rewrite it with the help of the secant stiffness of each spring. And once we know the secant stiffness under given boundary conditions, we can solve this shear span without problem. Now I want to talk about the constitutive relationships of those springs. First, I look at the rotational spring. These two springs at the end. Before any cracks appear in my beam, I assume the beam behaves elastically following motion co-theory until the first flexural crack appears in my end section. And then I have parabolic transverse curve to model the propagation procedure of those cracks. And then finally, I will have this critical diagonal crack when my tensile force in the longitudinal reinforcement reaches 2 times NCR. NCR is a cracking force of zoom influenced by bottom reinforcement. And after that, I can adopt 3PKT to describe the behavior of my beam. And the proposed relationship seems quite reasonable because it compares well with the experimental result, as you can see here. In this relationship, we also include unloading path. So before the formation of the diagonal crack, we assume there's no plastic deformation happening. Afterwards, we assume that it is parallel to the bell bar, right, the steel bar. This is very important, the post-peak, the unloading path, because it's important for the post-peak behavior, and also it's important for the load redistribution in continuous beam, which you will see later. And then we go to transverse spring. Even though in the macro element there's only one transverse spring, but actually it represents 4 springs in parallel, and each spring represents one shear mechanism along the diagonal crack. There are shear contribution from critical loading zone, from aggregate interlock, from stirrups, from double action. I will just look at one of them, for example, critical loading zone. As I told you, in critical loading zone, there's very high concentration of compression. Therefore, the behavior of critical loading zone is very similar as concrete under compression. Once we have the relationship for all the 4 springs, we can have the constitutive relationship for this single transverse spring. We assume that before the formation of this diagonal crack, the shear behavior is elastic, following Timoshenko theory, and then we have a sudden increase of deformation due to the unstable propagation of cracks. And then we can follow again 3PKT. Here I also include unloading path. So once we know well the secant stiffness, then it's easy for us to form a stiffness matrix for one macro element. And if we assemble several macro elements together, then we have the structure of simply supported or continuously supported deep beams. Under given loading condition, we can calculate the matrix of nodal displacements. From this matrix, I can read the displacement at each end of the macro element. With the help of this matrix called transformation matrix, I can calculate the three important degrees of freedom within my macro element based on the constitutive relationships I have just introduced. For the three springs, I can calculate the internal forces in my macro element, and therefore I can update the sequence stiffness. This procedure needs to be repeated many times until I reach, sorry, I forgot to do this, and until the convergence is reached for the sequence stiffness. And then I bring this sequence stiffness back to the element level. I repeat the entire procedure many times until convergence is reached at both levels, I mean structure level and element level. And I have applied this procedure to these simply supported deep beams. I model it with two macro elements. As we can see, even though these actually the two spans are identical, but the shear failure is concentrated only in the right shear span. What is the reason? We can explain this with the help of the macro element. Actually, this shear span, it goes into post-peak, and this one, it goes unloading. Therefore, this shear span. And here is a global shear behavior. Again, we can see that in terms of both pre-peak and post-peak regions, our prediction matches very well with the experimental results. And I have applied this procedure in the same way to many other beams. Here are the results. Here I show you a more complicated case, which is a continuous deep beam. It is symmetrical beam with two spans. Here it is a shear response, and it is very interesting to see that it is ductile, which is very different from what we know about shear. What's happening is because actually we have a redistribution of load between this shear span and this shear span. And this very beneficial action is very well captured by our macro element. So we are very happy about this. And for shear response, it's not only this load displacement relationship. Of course, there are many different aspects. For example, we can also look at the crack width in the diagonal crack here, and our macro element could provide a prediction for crack width at different levels, load levels. And this can be a very important, very useful tool, especially for existing structures, because we can measure the crack width inside, and then with this plot, we can estimate the current load level, and then compare with the load capacity, we can really know if our structure is safe or not. So until now, I'm only talking about beams simply supported, continuously supported. But as you know, my target is a large structure. It's a large frame structure. Therefore, I need to continue to move on, and I need to formulate mixed type modeling of structures with slender and deep beam elements based on the macro element I have just developed. Again, we see this large frame structure, and now what I'm going to do is to integrate these deep elements into a framework which has slender elements and is suitable for frame structure analysis. There are many options. There are many finite element softwares I can do it. And finally, we choose a program called Vector 5, which is developed in the University of Toronto, and it has been shown many times in literature for good prediction for shear critical frame structures. How does this program work? It is very similar as a solution procedure I have shown you in the previous chapter. It includes two levels of analysis. We have structure level, global frame analysis based on classical stiffness-based finite element formulation. And then we have element level nonlinear sectional analysis based on fiber section approach. So basically, the structure level, I can calculate the member deformation, and this member deformation then is imposed to each single element. Between these two levels of calculation, we will produce unbalanced force, and this iteration should go on until these unbalanced forces are close enough to zero. So for my mixed type modeling, I didn't touch anything of original vector 5. I only included one more subroutine in the fortune code for my deep beam analysis. As you can see here, again based on unbalanced force, I reach my convergence. With this procedure, I model this simply supported deep beam. Different from before, now I have 4-point bending. So here, this part actually is on the pure bending. Therefore, to model this structure, I will need a deep element for this shear span, and I need a slender element for this little part on the pure bending. Before looking at the results, I want to look at the convergence. How is the convergence? There are different options in vector 5 for convergence factors. Here I just show you the default one, which is based on the unbalanced force. Here you can see at each single load step, the convergence factor is close enough to 1. Here I also show you the iteration number. In each load step, it is much smaller than the maximum iteration number. Then for the sake of comparison, I also built 2D finite element model for each of the structures I'm going to study. This 2D finite element model is based on the program called Vector 2, which is also developed in the University of Toronto, based on modified compression field theory. And here, in the following two slides, are my results. So I have compared more than 20 beams. I have the green line represents the prediction from vector 2, the blue one from the modified vector 5, and this one is the experimental result. And as we can see, in most of the cases, that these two matches very well in terms of the shear capacity and the pre-peak behavior. The difference is in the post-peak. And my mixed type modeling, I think it's much closer to the experimental result than vector 2. And let's make one step further, because I want to study the large frame structure. So here, I have designed a frame structure based on ACI code. It's because it's very difficult to be tested in the lab, so there's no experiment done for this. And to model this structure, here I want to say more about this frame. So I have slender beams, and I have two deep transfer girders, deep shear spans here, and there are 20 stories, but I don't show them here. I model this frame structure with 3 different modeling strategies, because as we know, most of the load will be transferred in this deep shear span, so it is very logical and very practical if we neglect the upper part structure. Therefore, the first two models I use a simplified model, which only includes the bottom two stories, and the third one I build the entire 20 stories. Obviously, to build these three models, I need a different effort. But will the results also be different? Here is the answer. So here I show you the load displacement relationship. The displacement, I mean, it's a deflection in the first floor, and the load is a total load imposed in this structure. The blue represents the result from this simplified two-story frame, and the green represents the 20-story. As we can see, for the two-story simplified model, the 1D mixed type modeling result matches well with 2D finite element analysis for the peak load and the stiffness. But very surprisingly, that the 20-story frame model produces almost double the shear as the load capacity. This at the beginning I don't understand why, so I look at this plot, which is here I show you the load in each floor in a cumulative way. Obviously, in the first floor, because of the deep shear span here, it carries around 40% of my total loads, and in the upper stories, it carries very small loads because the slender beams are very soft. But even though it's very small, but we have many stories, so if we accumulate these small loads together, still it's a very big portion of the total load. Therefore, it is very conservative if we have a multi-story frame and we neglect the contribution of the upper stories. And at the same time, this kind of frame, it is very often be integrated with shear walls, and the shear walls will impose a lateral restraint to my frame. Therefore, to model this effect, I fix the lateral displacement of all those nodes. And here is my result. As we can see, both the capacity and ductility are improved. And finally, we can look at the computation efficiency. Here I have the computation time for 1D mixed type modeling for all the three types of structure. All my calculation is lower than 20 seconds. And in the other case, with 2D finite element modeling, my calculation can be as long as several hundred seconds. This difference is not huge if we look at the small structures. But if we look at the 20-story frame, I spent 6 hours in my office computer just to finish the computation. But I'm doubting if I can finish modeling this frame with finite element, the 2D finite element, in 6 hours. And even though I have a model, I may need many days to finish the calculation. Therefore, for large structures, this mixed type modeling is the advantage of this mixed type modeling is even more outstanding. To conclude, this mixed type modeling it can capture well the redistribution, the load redistribution, and the interaction between members in large structures, and at the same time it is very efficient. So we have good solutions for deep transfer girders. I mean solid deep transfer girders, and we have structure. So now let's change the topic. We can go to deep beams with web openings. This is a special case. So here I show you the experiment done by Malawi and Sharif in 2005. In their experiment, they have this square opening in the shear span, they have changed the location of the opening, they have changed the size of the opening. According to their observation, there are two different failure modes, mainly depending on the size of the opening. When the opening is small, we have two critical shear cracks above and below the web opening. And at the same time, we have some other cracks propagating either from or towards the corners of the opening. When this opening is large enough, we will have also a horizontal crack. In order to know more, to understand more about the behavior of those specimens, I have also modeled them with vector 2, and I have managed to get a very similar crack pattern as observed in experiment. I also look at the stress distribution. Here it is a principal compressive stress distribution. And I found it is very interesting that if I only look at this small area, both crack pattern and the stress distribution is very similar as in the case of solid deep beams. So I was thinking probably we can use some models for solid deep beams to model this small region. Therefore, we have this kinematic model, and in this green square, we have this small area. Now I call it bottom sub-shear span, and I try to associate it with 2pkt. I will express the distribution of the deformation pattern with two parameters, epsilon TB, and here I have delta CB, exactly as in 2pkt for solid deep beams. And if I reverse this deep beam, inverse it, I will have the same case as in the top sub-shear span. But still they are different. I will show you some difference between them. If I separate the two rigid blocks according to this diagonal crack, and in the top L-shaped regions, I have the top sub-shear span, and here at the support, I have a combination of shear force and compressive exile force. This is different because in normal solid deep beams, I don't have this compressive force, this exile force. I only have the shear force. To maintain the global equilibrium, I must have a same force as NT, but in the opposite direction. Therefore, in the bottom region, I have a tensile force. The value is the same as here, the compressive force. So here I show them in a simplified way. We have external compression here. We have external tension here. Remember the solution procedure for normal solid deep beams. We have the intersection between this red line and the black line. But now if we have additional compression, this solution will move upwards. With tension, it will move downwards. Therefore, based on this solution procedure, we can calculate the shear strength of the two sub-shear spans. Also, we need to look at this horizontal crack. I name this horizontal crack as crack A, and all the shear force goes through the top shear span will pass this section. Therefore, the capacity of this section is limiting the shear capacity of the top sub-shear span. And we need, in this section, we have both bending moment and exile force. To follow the classical way for slender beams, we can solve the capacity of this section. So to summarize all what I have said, we have five steps to solve this problem. First step, I need to isolate the two shear spans from deep beams, top and bottom. And then I solve the shear strength of the top sub-shear span based on 2pkt with additional compression. And then I calculate the strength of the section A. And then I calculate the shear strength of the bottom subshear span based on 2 pkt with additional tension. And then finally, I just sum them up in a very simple way. So I use this procedure to look at the effect of some important parameters. The first one I looked at is opening size. Here in this plot, I have M2, which represents a ratio between the weaponing depth and the beam depth. As we can see for this specific beam, we have when the beam depth, the opening depth increases from 30% to 50% of the entire beam depth, the shear capacity drops to half. And 40% of the shear capacity is carried by the top subshear span, and around 6% carried by the bottom subshear span. Another parameter I looked at is L/D ratio of the global shear span. Again, we can see that the shear capacity drops quickly when the beam becomes more slender. We have also plotted the prediction based on sectional model for slender beams, and normally we say the prediction for deep beams and the intersection between the prediction for deep beams and slender beams corresponds to the transition zone of deep and slender beams. Normally for solid deep beams, this value corresponds to around 2.5, but with the existence of web reinforcement, this L/D ratio is smaller. It's around 2 or 1.5, it depends on the case. And finally, I have implemented this procedure to all the 27 deep beams I can find in literature. In terms of shear strength experimental to predicted ratio, I have mean value equal to 1.03, coefficient of variation equal to 9.3. So that's all my research work in my entire PhD. So I would like to conclude it before the end. So what I did first, I have identified adequate models for shear strength of deep beams. I have formulated an efficient 1D macro element, and I have implemented it into different deep beams. And I have predicted complete shear response well. And I have established a mixed type modeling procedure. I use it to study the behavior of complex structures under extreme loading. And finally, I look at a special case, which is deep beams with openings, and I propose the solution for it. And in terms of future work, I have a few of the suggestions, and some of them are listed here. For example, we can study the shear failure after flexure yielding, and we can also include the effect of exile force in macro element. It's possible to study the entire behavior of reinforced concrete deep beams with web openings, and we could also extend applicability of 3 pkt. For example, we can study cyclic loading. And finally, I think it's very useful if we could propose a very simple design equation based on 3 pkt. So that's all about my presentation. Thank you very much for your attention.
Very good. Thank you very much for this very nice presentation. So that concludes the first part of the defense. So we'll now start with the second part, more precisely the questions of the jury members. And we will start with our external jury members and with Professor Yang first.